Maria. There you go. Here's Maria. Say hi. All right. In this video, I'm going to talk about this concept of torque. And I'm going to have Maria hold this broomstick kind of thing that I made, and I put some hooks in it. And she's going to hold it here. And I'm going to hang different masses on it. I have a 500 grams and I have a 1,000 grams, right? So I'm going to hang it in the third hook, and she's going to try to hold it and not allow it to fall down. You hold it? You got it? All right? Yeah. And I'm going to let her answer the question. Okay, how easy is it, or how hard is it?
Hard.
It's hard. Okay. Now I'm going to take the 500 and I'm going to put 1,000. So
Like,
hold
do
it.
I have to hold it in this?
Yeah, hold it.
Wait, hold on. I want to change my grip.
Okay, go ahead. And she can barely hold it. Okay, hold it up so that you can see. She can barely hold it. Hold it up. Hold it. Okay, so I have to kind of like give it a hand. So it starts to spin. So this idea of a force making something rotate is what we're going to call torque. So torque is the twisting effect of a force, basically. That's in your notes. So I'm going to go back to the 500 because she found the 500 to be easy, right?
Mm-hmm.
So I'm going to put the 500 at the third hook and look at it. Okay, it's very easy for her, right? Now I'm going to take this and I'm going to put it towards the end, and I'm going to let her tell you whether it's easier or harder than before.
It's way harder.
It's harder. You can probably see it in the video that you cannot see the stick anymore. So I think two things we have to realize here. Okay, so say bye to Maria. Bye, Maria.
Bye.
Okay. So two things we have to realize is not, okay, more force will create more torque, right? It will create more twisting. So when I hang the 1,000 grams at the third hook, it was harder for her than holding it at putting the 500. So the 1,000 created a greater torque. That's why it started to spin. With the 500, she was able to hold to have a counter torque, kind of, to not allow it to rotate. And then I went back to the 500 and I put the 500 at the very last hook, and it was very hard for her. Even though it was the same mass that was at the third hook, when I put it at the fifth hook, it was extremely hard. So I think this concept of torque that we're going to talk about definitely depends, or at least on these two properties that we're going to talk about. So the first one, I forgot to put on my microphone. Okay, so the first one is definitely the amount of force, and the second one is how far from the axis of rotation is this force applied. Because when we hold this, okay, this wants to spin this way, right? And we'll do this in class. It wants to spin this way, okay? So which means the axis of rotation is coming at you and at me. It's going to the board and to the back of the room, okay? You can do a lot of these examples with the torque. When you try to open a jar, okay, you're actually applying a force, okay, and the axis of rotation is kind of like right in the middle of this. It doesn't have to be real. It's a lot of times it's just virtual. So here I have a bolt, okay, make believe, okay, and I have a wrench, right? So in order to open the bolt, you have to create a torque. So you put the wrench around the bolt, right? And if you try to open, and the longer the wrench, the easier it is, because the point of application of the force is further away. So this whole thing is going to rotate easily. Just like when I did with the 500 grams on the last hook, rotation was easy, okay? The same thing here. So if my point of application of the force is the further away from the axis of rotation, which in this case is going up towards the ceiling and towards the ground, the further away you are from that point, the more torque you're going to create, okay? So distance is important. So that's why a lot of times when people have like something that's so tight that or rusted maybe, and it doesn't want to open, so like a bolt like this, so what they do, they use the WD-40, and if it doesn't work, they take a PVC pipe, well, it's like one of those white pipes for plumbing, and they stick it in here, and you go really far away, okay, and they're able to open it, or not always successful, but a lot of times it's very successful, okay? So that's pretty much the definition of torque. All right, let me look at my notes here. So we did the demonstration. All right, the other thing I want to talk about is a demo with maybe a door. And you know, my drawing skills are not the greatest. So here is a door, okay? And these are the hinges. This red line is where the hinges are, right? So this door opens and closes this way, right? So it goes into the wall and comes out towards me. Okay. So okay. So if I push on the door right here, and we'll do this in class, you're gonna feel that it's harder to open the door, right? In other words, more torque is required, okay? If I try to push at the end here, okay, of the door, it's easier, okay? So a wider door is easier to open. It doesn't require as much torque as a narrower door. And another example that I would like to give you is like if you're going into the F wing, there is like a wider door and there is like a tiny door, right? So the tiny door, if you ever try to go through there, it's always harder to open that door because you're right at the axis of, you're very close to the axis of rotation. Well, what happens if I apply a force at the axis of rotation? I will not get any torque. So any force that's at the axis of rotation or going towards the axis of rotation, hitting it in other words, is not going to create any torque. So it's like coming here and pushing on the door, coming to the end of the door and pushing towards the hinges. So if I apply a force this way, going at the axis of rotation, I'm not creating any torque. So you have to be at a certain angle with respect to the axis of rotation, okay? All right, so I talked about all those ideas. Okay, so now so if you want to create maximum torque here, you have to increase your distance away from the axis of rotation. So this, I think I'm going to call this R or D, and I have to push, okay, or pull with the maximum force. In that case, I will have maximum torque. So definitely this idea of torque, which is Greek letter tau, is definitely going to have the force in it, and it's going to have that distance. We'll call it R or D. It doesn't matter. But I think there is another factor that we have to bring in here. What happens if this force is not acting perpendicular to the door? So let's just take, let's say I'm pushing. Okay, let's go back to the same door. Okay, here are the hinges here. And this time, instead of pushing into the wall or into the board and out, I'm going to push at an angle, let's say. Maybe I should do this just with a mirror stick. It's probably easier to do. So these are the hinges. So let's just say, oh, these are the hinges on my left. So let's say this stick can rotate this way. Okay? So now if I push from here, it should be harder. If I push from here, it should be easier to rotate. Okay? If I apply a lot of force, it's going to be even easier because I'm going to create more torque. Well, what happens if I come in here, but I don't push at a 90-degree angle with the ruler? I push at an angle like that. Okay? So here is my stick. And this is the axis of rotation. We usually do a dot or an X. So the axis of rotation is coming at you. I'm sorry, the computer is misbehaving. So what I was saying is like now I'm not going to push at 90 degrees. Okay, I'm not going to push straight up. Okay, and I'm not going to push towards the axis of rotation. What I'm going to do actually with this stick, this mirror stick, I'm going to push at an angle like that. Okay, or I'm going to pull at an angle if I had a piece of rope in there, right? So this force that I'm going to pull with or push with can be broken into two components. A vertical component, I guess in this case, and a horizontal component. Okay, or you can call them perpendicular and parallel, whatever you want to call them. Okay? If you notice, this FH, or this component of this F, does not do any torque because it's directed right at the axis of rotation. So the only one really that does anything is this V. And that's applied here, by the way. I just draw the triangle there. Okay? So this angle here is going to matter. That angle is theta, right? Now let's see how this works. So I think FV is just going to be F times sine of that angle. Which means that I can add the sine of the angle here. Now, the angle theta, you have to be extremely careful, is the angle between what we call the lever arm, this R, okay, and the applied force. Okay? So here is the arm, here's the force. The angle between them is what you're going to put in there. Okay. Well, what happens if someone is pulling with the force this way, and this angle here is theta? Okay. Well, you're gonna get the same torque, because this is the lever arm, this is the force. They make an angle theta between the two of them. Even if you don't want to do it that way, you can look at this angle if you like. Well, that's 180 minus theta, and supplementary angles have the same sign. Okay, so this is between lever arm, R, and direction of force. Okay. All right. So we're going to try to do this a different way. So I'm going to go back here and put my force F. Okay, so if I extend this force, this is what we call the line of force, okay? The only thing that matters is how far is this line of force is away from the axis of rotation. So basically, this here is the distance, okay? This is a different R we're going to add to it, is the distance between the axis of rotation and the line of the force. And you know, to find the distance between a line and a point, you have to go at 90 degrees. Now, if this here is theta, okay, and if this is 90, that's your hypotenuse, right? So I hope you can see that this R is R sine theta. So sometimes we call this the R perpendicular. Why do we call it perpendicular? Because it's perpendicular to the line of the force. So in that case, you would just do F times R perpendicular, right? So another way of writing torque is F times the perpendicular component of the R. Why is it perpendicular? Because it's perpendicular to the line of force. Okay. All right, let me see what else I have to talk about. All right, last thing is the nature, the vector nature of torque. Well, the vector nature of torque, direction of the torque vector is the same as the direction of the angular velocity. Sorry, I made a mistake. I meant to say the direction, or the vector torque has the same direction as the vector angular acceleration, not angular velocity. Thank you. Okay, and I think I pretty much covered everything we need to know about torque. Okay. I mean, there are a lot of other examples. Okay, so here. So I'm going to use this as an example, actually. So a truck has a large steering wheel, right? That's why you see a lot of those truck drivers, if you ever seen them, when they want to turn, they apply very little effort here. They have little effort at the end, okay? And the reason for that is because in order to turn this steering wheel, this is really far away from the axis of rotation, which is coming at you and coming at me. So they don't need to apply a lot of force because the distance kind of like helps. But if I try to turn this bicycle wheel from when I'm closer to the axis of rotation, I'm going to feel that there is more effort required. So think of it as like the steering wheel for a car. You need more effort to turn it than you do for a truck. And that should do it.
All right, I'm out. Peace.